Hello everyone, today we're going to talk about complex zeros and the fundamental theorem of algebra a little bit. So complex zeros now, we just learned about complex numbers. So now we're going to learn about the complex zeros of polynomials. So those will be the zeros that you get of, let's say, like a fourth degree polynomial that do not come out as a real number, right? So they were like the negative under the radical when we did those quadratic equations, right? When we did the quadratic formula. So this is what we're going to do now. We're going to find those complex zeros. So the first one, they want us to find the zeros by first factoring. So to start off factoring, this fourth degree polynomial factors into x squared, right? Instead of like when we normally have a quadratic, we would factor x and x. So we have a fourth degree, so I'll just do x squared and x squared, same difference. And plus 5. Right, so we can see that if we FOILed this back out, we would get back to this quadratic. Now we can see, okay, x squared plus 5, that really doesn't work for us. So they say use the quadratic formula, but we know that these must be equal to 0. So if I subtract the 5, x equals plus or minus, right? Whenever you take the square root of a number, we get the positive and negative version of that number, radical 5i. And we pull the I out so that we no longer have a negative under the radical. So that gives us 2 zeros for this factor. And since the other factor is just the same, right, that means we're just going to have 2 duplicate roots. So all together our zeros, we have positive square root 5i, and I won't even write the positive because that's normally not how we write it. So we just have square root 5i multiplicity 2. And we have negative square root 5i multiplicity 2. So there we go. We factored it and we found all of the solutions. They happen to all be complex roots. So there's no real roots on this, meaning if we graphed it, it would never cross the x-axis. Next, they give us a polynomial. They want integer coefficients. So if for some reason after we FOIL this all out, we end up with a fraction somewhere, we have to go through and multiply by that denominator to get rid of that fraction because they want all of our coefficients to be integers. So I don't foresee that happening because we don't have any fraction zeros. So let's go ahead and FOIL this out. So the key thing here being it gives us a complex zero. So when we have a complex zero like that, we get the actual x minus 1 minus 2i, right? So we get that one, and we also get x minus 1 plus 2i. So whenever we have a complex zero, we also have the negative conjugate, which we did when we talked about complex numbers, right? This is always, whatever our zero is, it's always x minus that zero. And it says 1 has multiplicity 2. So just like with the 1, right, x minus 1, I'm going to do the same thing with the complex number. X minus whatever that complex number is. X minus whatever that complex number is. Okay, so it looks kind of funky having like 3 terms in there, but you'll see as we FOIL it out, a lot of stuff will cancel, and we'll get rid of the imaginary numbers. So as I go, and I'm going to simplify one more time before I FOIL it out. So I get x minus 1 plus 2i, right, if I distribute that negative sign. And then x minus 1 minus 2i, if I distribute that negative sign. And then I still have my x minus 1 and my x minus 1. So continuing on, I'll FOIL here. So when I FOIL, I'm going to do this in, let's see, no, I'll continue. So when I FOIL x times x, x squared, x times negative 1, negative x, x times negative 2i, negative 2xi. Then I'll move on to my negative 1. Negative 1 times x, negative x. Negative 1 times negative 1, positive 1. Negative 1 times a negative 2i gives me a positive 2i. And I keep going. 2i times x is a positive 2xi. 2i times negative 1 is a negative 2i. And 2i times a negative 2i is a negative 4i squared. So I'm just going to show this simplifying, and then I'll carry my x minus 1 times x minus 1 down. So foiling out these two terms give me all of this. Looks a little scary, but it's not so bad because a lot of things will cancel. Here we have a negative 2xi, positive 2xi. Positive 2i, negative 2i. So now when I simplify a little bit, I get x squared minus x, and I have two negative x's. And here I have a positive 1 and minus 4, but remember I squared is a negative 1, so that's really a plus 4, so I end up with plus 5. And now I still have my x minus 1s, so I'll carry those down. I think it's easier to FOIL a 3 term with a 2 term than it would be to FOIL these out and then distribute all of those. So I'm going to take this 3 term and I'm going to multiply it by this 2 term. So that's going to give me x cubed minus x squared minus 2x squared plus 2x plus 5x minus 5. And I still have one more x minus 1 to distribute in. First, let's simplify. So I only have one x cubed term. Here I have a negative x squared and another negative x squared. So that should give me, negative 2, so minus 3x squared. Here I have a positive 2x, positive 5x, and negative 5. Okay, and then I multiply that by x minus 1. And one more time, I get x to the 4th minus x cubed minus 3x cubed plus 3x squared plus 7x squared minus 7x minus 5x plus 5. So last time I will simplify to get the final polynomial, and I get x to the 4th. Here I have a negative x cubed and a negative 3x cubed, so I end up with negative 4x cubed. Here I have a positive 3x squared, a positive 7x squared gives me a positive 10x squared. Negative 7x, negative 5x gives me a negative 12x plus 5. And checks. That is the polynomial, 4th degree polynomial. Right? They say it has 4 degrees, so we have a 4 degree. It started with the complex zeros, 1 minus 2i and 1 plus 2i, and had 1 as a double root, multiplicity 2. Let's move on to the next one. They want us to find all of these zeros. So first, let's write all the possible zeros, right? P divided by Q. Well, my Q is just 1, so I'm only going to have the factors of 12. So I get plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, or plus or minus 12. So let's go through and check. Like I said, I like to start with 1. It's the easiest one to check. So P of 1. P of 1 gives me 1 to the 5th minus 1 to the 4th plus 7 times 1 cubed minus 7 times 1 squared plus 12 times 1 minus 12. So let's see what this gives us. This gives us 1 minus 1 plus 7 minus 7 plus 12 minus 12. They all cancel. We get a 0. So cool. 1 is a 0 of this polynomial. So let's go through and synthetically divide it. So our coefficients were 1, negative 1, 7, negative 7, 12, negative 12. So I carry my 1 down. 1, 0. 1 times 0 is 0. Carry the 7 down. 1 times 7 is 7, 0. 1 times 0 is 0. Carry the 12 down. 1 times 12, 12, 0. Okay, so now I've synthetically divided by the one number that I knew was a 0, a 1. Let's see what we have left. So after I do that, I have a constant of 12, right? I have no remainder, so constant of 12. I have no x term. I have 7x squared. I have no x cubed term. I have x to the 4th. Makes sense that I have x to the 4th because I started with a 5th degree. So when I divide by one factor, I should have a 4th degree left. Giving me x to the 4th plus 7x squared plus 12. And if you do a little tinkering, you can see that this factors. So again, this factors with an x squared plus 3 plus 4. Right? And if you FOIL this back out, we would get that. If you FOIL this back out, we get this polynomial. And we can see here that these are definitely not factorable. So I'll let x squared plus 3 equals 0 and x squared plus 4 equals 0. So I subtract my 3 over, x squared equals negative 3, square root, x equals plus or minus radical 3i. And same thing over here, x equals negative 4, x squared equals negative 4. So square root x equals plus or minus radical 4i. Okay, so here we only have one real root. We have the positive 1 as a real root, and then we have 4 complex roots or imaginary roots. So if I were to say the zeros, which is what we're looking for, I have 1, then I have radical 3i, negative radical 3i, and then a radical 4, I didn't even simplify it, but that would obviously simplify to plus or minus 2i, right? Radical 4 is just 2. So that would leave us with the roots 2i and negative 2i. So those are my zeros. That is all they asked for, but just if I wanted to show the factors would look like, that should be an R, not an N. Look like an N. So the factors would be x minus 1, x minus radical 3i, x plus radical 3i, x minus 2i, and x plus 2i. So those are the factors of that 5th degree polynomial that we started off with. And lastly, find all the zeros here. I'm doing this one more time, so it's a little repetitive compared to the last one, but this gives me at least 2 real zeros. So it gives us a little more practice. So again, all my possible zeros, well, my leading coefficient is 1, so I only have to worry about the zeros of my p, which is plus or minus 1, plus or minus 3. And I like to start with 1, so I'm going to plug p of 1 in. 1 to the 4th, minus 2 times 1 cubed, minus 2 times 1 squared, minus 2 times 1, minus 3, gives us 1, minus 2, minus 2, minus 2, minus 3. So when I do that, that gives me negative 8. So 1 is not a 0. So then I'll try negative 1. So p of negative 1 is negative 1 to the fourth minus 2 times negative 1 cubed minus 2 times negative 1 squared minus 2 times negative 1 minus 3. Gives us, well, negative 1. A negative to any even power is going to make it a positive 1. Here I have a negative 2 times, well, a negative number to an odd power, right? That's going to keep it negative, so I really get plus 2. Negative 1 squared is going to turn into a positive 1, so that's going to stay a negative 2. And here 2 times negative 1 is going to make that a negative 2, so a negative 2 is plus 2 minus 3. So here I've got 3 minus 2 is 1, plus 2 is 3, minus 3 is 0. Negative 1 is a 0. So go ahead and divide synthetically by negative 1. And my coefficients were here. You can go back and check. Those are the coefficients I get. So 1, negative 1 times 1, negative 1 gives me a negative 3. Negative 1 times negative 3 is a positive 3. Negative 2 plus positive 3 is 1. Negative 1, negative 3, positive 3, 0. So after I do that, that leaves me with the third degree polynomial now, because I divided through by a factor, started with a fourth degree. So I'm left with x cubed minus 3x squared plus x minus 3, remainder 0. We proved negative 1 was a 0. Now, I can't factor this yet, so I've got to go through and try the zeros again. But as we've learned, hopefully so far, I do not have to check number 1. I do not have to check positive 1 again, because it didn't work for the first one. So if you check a couple zeros and it doesn't work for the original polynomial, it's not going to work after you've synthetically divided by one of the zeros. So I don't need to check positive 1 again. So I'm going to start with negative 1, because that one worked before. So maybe it's a double root, so I'll try it. So I get negative 1 cubed minus 3 times negative 1 squared plus negative 1 minus 3. So negative 1 cubed gives me a negative 1. Minus 3 times negative 1 squared gives me negative 3. Plus a negative 1. Plus a negative 1. So, and then minus 3. So this gives me, again, negative 8. So now negative 1 is not a 0 of this. So I'll move on to my next possible 0. Since I've already taken care of 1 and negative 1, I'll start with a positive 3. So I'll do p of 3. So that equals 3 cubed minus 3 times 3 squared plus 3 minus 3. So that gives me 27 minus 27 plus 3 minus 3 equals 0. Cool. So that means our other real root is a positive 3. Let's go through and synthetically divide by 3. And my coefficients were 1, negative 3, 1, negative 3. Carry my 1 down. 3 times 1 is 3, 0, 0, 1, 3, 0. So we've proven 3 is a 0, and we are left with x squared plus 1. Well, x squared plus 1 is not going to factor, right? And if we know x squared plus 1 is equal to 0. So to solve for x, we get x squared equals negative 1. Take the square root of both sides. So we get x equals plus or minus. Square root of 1 is just 1, right? So it would be 1i, which we can also just write as x equals plus or minus I. Right? No reason to write the 1. So they wanted us to find all the zeros. So the first 0 we found was negative 1. The second 0 we found was 3. And then, as always, whenever we have complex roots, whenever we have imaginary numbers, we're going to get the positive version of that complex number and the negative version. So the complex numbers always come in pairs of 2. So we get a positive I and a negative I. So those are my zeros. Okay, so go ahead and try the example problems that accompany this PowerPoint, and we'll talk about this next class.